What I'm going to talk about is on the 5-4 model. And the 5-4 model is a spin model, which I will see is closely related to the Ising model that maybe some of you are familiar with. But just to be sure that we're on the same page, I'm just going to first tell you why we're interested in the Ising model. Oops. Okay, so there is a very interesting phenomenon that was represented by Curie and possibly by Ising before him, where if we take a magnet and some metal, let's say some piece of iron, of course, as you all know, if you bring them together at room temperature, then they will attract each other. And in fact, the iron will stay magnetized even after you remove the magnet, at least for some amount of time. But now, let's see what happens when you increase the temperature. So if you increase the temperature a little bit, then you will still have the same behavior. But if the temperature becomes very, very high, then suddenly, once you remove the magnet, the iron won't stay magnetized. Okay, so this is what we call a phase transition. You go from a phase where the iron stays magnetized to a phase where it doesn't stay magnetized once you remove the magnet. So that's the first transition that we're interested in. And Lenz was probably the first to try to introduce a mathematical model for studying this phenomenon. And that was later studied by his student Ising, and the name came from his students. So maybe that's the dream of every PhD student here in the audience, to have a model named after them and not by their supervisor. And okay, so that's the history. Now, the Ising model, how is, I'm going to give you the formal definition now, just very definition. So what we do is we take our lattice ETV, and its vertex has some spin. It takes two possible values. It can point to two possible orientations, let's say either up or down. And now you sample configurations in some sort of random way, coming from some probability measure. And then what you're interested in is whether, well, most spins will point towards the same orientation or not. And if yes, then you say that you're magnetized, otherwise not magnetized. So that's the idea. And the Ising model has been studied quite a lot. And what I'm going to talk about today is a generalization of the Ising model for the 5-4 model, where spins don't only have orientation, but they also have magnitude. So they take values over R. So here is the formal definition of the model. I'm going to start with the case of a finite graph. So we're saying random variables to the vertex of our graph. And these random variables, they take values over R, and they are correlated. And the density is given by this formula. So you have this exponential of beta phi x phi y over all edges of your graph. Here beta is some parameter, which you should think of as the inverse of the temperature in this experiment that I tried to explain. And okay, our spins take values over R. So we need to try to control their values so that they don't take a very large value. So we also have this single head measure, which has density, which is exponential of minus some even quarter polynomial, and hence the name of the model. That's why we call it 5-4. Okay. And then, of course, in order to make this probability measure, we also need to divide by some normalization coefficient. So that's the definition of the model. Does it make sense? Are there any questions so far? The definition? Okay, and just the definition so far. So here in this talk, we will always assume that our beta is positive. So this means that we are in what we call the ferromagnetic case. So if you have two neighboring spins, they tend to align to each other. They tend to take values that are close to each other. And perhaps one way of seeing this is by writing this same phi x phi y in this way. So here you see the square of the difference. So this is that you're penalizing large differences. So that's why neighbors tend to be close to each other. Okay, so that's the definition of the model. Now the 5-4 model separates between two very famous models of statistical mechanics, where one of them is the Ising model that I just mentioned, and the other one is the Gaussian free field. So how do you define the Gaussian free field? Well, formally you define it by taking this constant here, g, to be equal to 0. In this case, of course, if you get something pi squared, so you get something Gaussian, all right? But okay, you need to be careful and you need to take the right value of A in order to get something meaningful. So if, let's say, A is beta times the degree over 2, then you get the massive Gaussian free field. If it's larger than the value, then you get the massive one. And if it's more than this value, then well, you get nothing because these integrals don't converge. Okay, so you don't have a model if A is small enough in this case. And so yeah, in this way you can get the Gaussian free field in this way, and you can also get the Ising model as some sort of limit. So what is the idea? You can take, for example, A to be this very precise value minus 2g, and what does this do is that this polynomial here, this quadratic polynomial that you have here, it becomes a double wave. It gives more and more mass to plus minus 1 as you send g to infinity. And so in the limit, all your spins take values plus or minus 1. And so in this case, you just recover the Ising model. Okay, so you can think of it as the definition of the Ising model if you wish. Okay, so this is just maybe one reason why I went in the 5-form model. Okay. Good. Now, what are the origins of the model? Well, the origins of the model are in the continuum, they're in physics, in quantum field theory, which is something I'm not an expert on, so I don't want to look too much into the details of that. But basically, the idea is that physicists don't like Gaussian fields because, according to them, they correspond to a theory of particles that do not interact with each other. So they would like to have a non-interactive particle theory. So an interactive particle theory, and they try to come up with this 5-form model. And why 5-4? Because 4 is the next integer, which is even, and it's larger than 2. So that's why this is somehow the simplest candidate for a non-Gaussian theory. And well, as you can imagine, constructing these fields can be very difficult in general. And one way to construct is to start from the discrete and then take some sort of limit. And so this is how the discrete 5-4 was defined. But as it turns out, the discrete 5-4 model is interesting on its own right. And this was first observed by Griffiths and Simon, who put the following result. So it's about the Ising model on the complete graph on n vertices. So you consider the model on the complete graph on n vertices at this critical window. So you have some parameter which is 1 over n. So basically around 1 over n is where something interesting happens in the model. And okay, you have this critical scaling lambda over n to the 3 over 2. Lambda is some parameter, can be any real number. And then what they proved is a central limit theorem for the sum of all these spins in the complete graph, except that you don't divide by square root n, you divide by n to the 3/4, and you don't converge to the Gaussian. You converge to this distribution. So you see again this exponential of minus this quadratic polynomial, and here you see this parameter lambda, which you also see here in the parameter of the model. Okay, so this is what they proved, and in fact one can see from that okay, this is basically some sort of trivial 5-4 model. It's just a 5-4 model on a single vertex. So that's interesting maybe so far. And this is maybe the point I would like to draw a picture, but maybe we'll just try to explain in words. And you got the pencils. So then let's say that you want to approximate your 5-4 model on a finite graph. Let's say that this is the graph, it's the square. Then what do? So if you want to get the 5-4 model here, so you start from Ising on this graph where you blow up each of the 4 vertices into the complete graph. Okay, so here you have Kn. And then you put all possible edges between neighboring blocks. So you can define the Ising model on this graph with certain parameters. So the parameters inside each block, they are the same as before. Between blocks, they are different. They're coming from this parameter Cm squared, which is basically of order, something of order 1 over n to the 3 over 2. Inside the blocks, they are basically of order 1 over n. And then what one can prove is that if you take the average of all the spins inside this block, you normalize the property, then you converge to pi. Does this kind of make sense? Yeah, so you now just go from telling about what happens just on each block to telling about the whole thing. So jointly you converge to phi 4. Okay, and so now if you are a physicist and you see this, what do you say about this result? Well, you say, well, since the phi 4 model is the limit of Ising models, well, these two models should behave in somewhat similar way. They should share a lot of common features, and if you're familiar with them, they would say that the phi 4 model is in the Ising unit chapters. If this means something to you, that's fine. If not, maybe I will try to explain a little bit what it means in a while. But okay, what you should expect from this is that Ising and phi 4, they should behave in a somewhat similar way. Okay, they should share a lot of common features. And one of the first things that we learn about the Ising model is that it goes a phase transition. So let's see how this manifests itself in the case of the phi 4 model. Okay, so in order to see a phase transition, we need to go to infinite volume. So we start from a finite graph, now we want to go to an infinite graph. And we would like to understand somehow how infinite volume measures behave. So how do we define our finite volume measures? So now, at the beginning, I defined the model with no boundary conditions. So here I'm going to introduce some boundary conditions, which you should think of as, at the beginning, I told you that, okay, you have some magnet and some metal, and then you remove the magnet and something happens. Kind of the same thing. You have some boundary conditions which have this effect of introducing some sort of magnet to the system, and then you try to remove them by sending your graph to infinity and see what happens. So that's the idea. And so here I'm going to introduce these boundary conditions. So what does this mean? That okay, I have some fluid size, some random values, fix some values outside of my graph, and then I'm going to add to my definition of the measure this term which takes into account the interaction with the boundary. Okay, so I have again some beta, phi x, psi y. X is inside my domain, y is outside of my domain. Okay, so this is how I define the model with boundary conditions. I should just add this extra term. And now what you have to do is send your graph to infinity the whole of ZD. So we're going to work on ZD. So all the graphs that we're going to consider are going to be subject of ZD that grow to cover the whole ZD. And you will understand this infinite volume measure you're going to get in this way. And in particular, what we get to understand is the maximum measure. So you're going to have a whole family of measures. Can you understand the maximum measure? If you can understand the maximum measure, maybe it can tell you something about all other measures in this family. Okay, so we wanted to define what we call the plus measure. And in the case of the Ising model, defining the plus measure, defining a maximum measure is kind of intuitively clear how you should do it because your spins take values plus minus 1. Plus 1 is larger than minus 1. So the plus 1 by the conditions should be the largest one, right? But now in the case of the phi 4 model, spins take values over R. So there is no maximum, right? So how can you deal with that? Well, maybe you cannot define a maximum measure at finite volume, but maybe you can define a maximum measure at this midpoint. And what is the idea here? The idea is that let's say you imagine you have an infinite volume measure, and this infinite volume measure, its spin, its random variable has some moment which is kind of analogous to the moment that comes from the single set measure here. And so it has, you have the expectation of it, then minus some constant. So you can imagine that.
Can you say a few little words about what you mean by the maximal measure?
In terms of stochastic combination.
You want to try the other microphone if it's on?
Sure.
Maybe it works better.
Right. Sorry. Yeah, so you want to construct the maximum measure of stochastic domination. Right, so at its vertex, you want your spin to stochastically dominate any measure from this family of potential infinite volume measures can be defined. And well, since at finite volume, you have this term here, this should tell you that if you like a sort of expectation of your spin at the origin of this, maybe let's put here G/2. Something like this should be fine. It is not to expect to have something like this at infinite volume. And if you have an estimate like this at infinite volume, then Bohr can tell you, that, well, you are supported on configurations that don't grow too fast. They grow at most like some constant times 4 to the floor. Just to be the volume basically of the graph, that's why you take this 4 to the floor here. And so it would make sense to define this to be your maximum bounding condition 5. Okay. And then indeed we can show that if you define this to be your plus measure at finite volume, with some constant here m which is large enough, then indeed you have a limit, and this limit satisfies the condition, so there is some sort of self-consistency. And where does the maximality come from? You can, instead of m, you can take, for example, 2m, and some other sort of larger constant, and you always converge to the same measure. So this is where the maximality will come. Right, so you basically you need to restrict yourself to something, some bounding conditions that don't go too fast, because otherwise you wouldn't even have tightness of your measure. So that's kind of the idea. Okay, so in this way we define our plus measure, and now what we're interested in is what we call the spontaneous magnetisation, which is just the expectation of your random variable to the origin. Okay, these funny symbols are just expectations. This is how we make expectations of the mechanics. Okay. And yeah, you should think of it if this quantity is positive, you should think that this means that even if after you remove the magnet, you still have some effect to tell you that your spins are more likely to be positive than negative.
So this you can do in any
Yes.
Okay.
Yeah, you can do. Yeah, you can do on Z, and yeah, have a PDC of course try to do it on any graph basically.
Okay.
So the growth of the graph somehow plays a role if you want to go to something that goes too fast. Faster than polynomial. Yeah.
Your graph is always embedded in a flat space, right?
Yeah, just Z. So the coordinates just are the integers.
Okay.
So yeah, you got linear space. So you just extend your graph.
Yeah.
Is a degree.
So you cannot. This doesn't extend, for example, if you live on an Eigen
So you
or on a sphere.
so you can so of course you want to work with infinite. You have one set of mechanical graph and go to infinite graph. So as long as okay, so what my PhD student is proving now is as long as your graph let's say has bounded degree,
Okay.
you can
Oh, okay,
define it.
okay, thank you.
Yeah, and maybe that's okay. So maybe I should ask an interesting question now, since you just asked me a question. So what do you think is the limit for tightness of the measure? So how large can you take the boundary conditions and let's say on ZD and still have a measure, probability measure. So I can give you some options. So the limit is something logarithmic. The limit is polynomial, it's exponential or super exponential. So who thinks that it's polynomial?
In what choices you can make for the C?
Yeah.
Will then allow the limit to still be a probability measure.
Yes, exactly.
No.
I would fail.
So the answer is
Oh, wait. There's a key there.
so the answer is that
I'm supposed to plug it into that formula, right? That expectation needs to be finite, right? Is that what I'm supposed to plug it into?
so
I
here.
want that, right? So I need that. Is that what I'm supposed to do, or is that wrong?
So the limit is double exponential, especially with the 3 here. 3 is just 4 minus 1. So I'm not sure if there is an easy way of seeing this, but the idea is it just boils down just solving such an equation. A is some parameter, and you see that basically when you go from one layer to the next, like if you have some large value here, let's say if you have some value x, 8, and you just to the next layer that's inside, your value of your mean is going to go to drop by a power of a third. That's why some sort of solution coming from this equation, which is what we're doing with my PhD student. So yeah, this is how you see this.
And so why are you calling it plus measure?
So this comes from the case of the Ising model where you have two spins like values +1 or -1 and plus corresponds to +1. So we're going to see this as sort of +1 measure, some sort of positive measure.
Okay.
But of course here, because our spins are bounded.
Yeah. So this is the analogy to if you set the boundary, all of the boundary spins in the Ising model to +1.
Yes.
You say that you're supposed to connect this limit to that.
Yeah, exactly. And this is just an abstract definition. Of course, even if you take here +1 of the conditions, you still get the same measure. Or +2 or +0.5 or any positive number, you should always get the same limit. This is more difficult to prove. And so far, now we know how to prove it everywhere except maybe what I'm going to define now, which is the critical points. But in general, this up to this point, I'm just doing some sort of abstract stuff just so that I'm able to get some sort of feeling, which is nice. Any other questions? Yeah.
If this is a waste of time, ignore me, because I'm really sorry about this. I just want to double check. Edges are nearest neighbors. Edges,
Yes.
they all have the same positive value of 1. Am I right? The connection strengths are all 1.
Yes. So you have the beta here, which
Yeah, no, I've got that. And then the thing that's, and I'm sorry, this is not anything I understand at all.
Yeah.
The 5 to the 4 term,
Yeah.
that you've integrated, you've summed over all, everything, everywhere.
Right.
So that doesn't change as lambda changes. But the other 2 terms, the middle and first term, do change. as
sorry,
lambda
it should be a V, it should be a lambda. Yeah, that's right.
That was really confusing me.
Right. I moved between 2 different notations, lambda and V, and
So this is all now local to a lambda,
yes.
except the middle term, which is somehow, you've written it in a slightly odd way, but basically that's bringing in inference from outside lambda into lambda of C.
Yeah, exactly. So here you have lambda, your domain,
Yeah,
and these are This is just the boundary, the external boundary of the thing we have outside. And
Well, it's not even the boundary, it's everything outside.
it's everything outside, yes, but okay, the way defined is that you have this notation which
Oh,
means,
they're
which
local,
means neighbors.
they're local edges. Right, I get you. So the edges are just the nearest neighbor. Sorry.
Yes,
You were speaking the question. Thank you,
Yeah.
thank you. So B should be lambda.
yes, usually lambda, yes, yeah, I moved to different notations and then. And any other questions? Okay, so then let's move on. So now that we have defined our magnetisation, well, the magnetisation as we want to study magnetisation as a function of beta, so it's always a non-negative. They always non-negative value because of the last boundary conditions, right? So if I had no boundary conditions, if everything was zero, let's say outside, this expectation would be zero just by the symmetry of dimension, because atomic symmetry would be even. So without putting any boundary conditions, I would get zero expectation. But in this case, because I have positive boundary conditions, I will get something which is non-negative, and it's also increasing in beta. It's for some sort of correlation inequalities. And so we can define the beta C of our model, the critical point of our model, which is the first point above which the generalization becomes strictly positive. Okay. So that's the definition of the model. You can solve the critical point of the model, and you can give this definition in any dimension. In dimension one, everything is kind of trivial, and beta Z tends not to be infinite, which means that magnetisation is always zero, no matter the value of beta. But in dimensions 2 and above, beta C tends not to be non-trivial. So it's strictly positive and fine. And this was proved by, okay, it follows from the so-called pi exactly. Okay, and yeah, so this is the definition of the critical point. We don't know a priori the value of beta C. It doesn't seem like any interesting value, maybe for dimension 1, or maybe if you change the graph and you make it x3, maybe you can do some calculations and find the precise value of beta C, but on ZD, doesn't seem to take any interesting value or any value that can calculate. So we learn the value of beta C. But we still would like to understand the model. As beta C below beta C above beta C. Another thing that this definition doesn't tell us about the model is what happens at criticality. So if you look at this definition, the definition tells you that the magnetisation is zero below beta C, strictly below beta C, is strictly positive above beta C, strictly above beta C, but at beta C, we don't know whether it's zero or whether it's positive. If it happens to be zero, we'll say that we'll have a continuous phase transition, but for obvious reason, because then the magnetisation is a continuous function of beta. And otherwise, I would say that it's discontinuous. Okay. And of course, yeah, as I said, there are three different phases we studied. The phase below beta C, it's called the subcritical phase. The phase above beta C, supercritical one, and the critical one at beta C. They're all interesting on their own right. And yeah, there's somehow some different methods to study the model depending on where you are in the phase diagram.
So I guess you already know a priori it's left or right continuous or something.
Yes, you can prove that this is right continuous by some sort of correlation inequality. We say that it's a decreasing limit of increasing continuous functions. So every such thing is continuous on the right. So there's some sort of way of saying that yeah, it's continuous on the right. And yeah, if the value of at is going to be zero, then you are really continuous. Any other questions?
So continuous on the right means you're raising temperature.
Yeah, so
That's
as
raised temperature.
yes, so the limit from the right, so the limit as you go to beta C from the right,
The picture's inverse temperature.
this thing. Well, you can go to CO2. So this can also prove.
So is there an example where someone proved that a phase transition is continuous, but they didn't know what PC was. Let's say I was doing bond percolation on D equals 2. I didn't know PC was a half. Would I have a chance of proving this continuous at PC if I didn't know it was a half? If I don't know the value?
Well, that's an interesting question. So for Bernoulli percolation, we do know the value.
We do know the value.
It's 1/2. And if you look at generalization, so for a lot of other models, like Boolean percolation or that's some case where we do know the value, that's some case where we don't know the value. And there is a general way of proving dimension 2 that you have a continuous transition. And we get crossing probabilities and what we call RSW theory. So there is a way, doesn't always work, but
So I can do it without knowing what I have.
yeah, you can do it without knowing that it's a half. And yeah, I will show you a theorem later on, but you can also do it in higher than not only in dimension 2. Yeah, any other questions? Okay. But okay, so now let me just mention some interesting results in the statistical model. So as it turns out, the subcritical phase of the model is well understood. So if you are below beta C, the magnetisation is 0. And basically what this tells us is that if you take two weights which are very far away from each other, and you get the correlation, then the correlation goes to 0. Right? If you take a distance to infinity, the correlation will go to 0. This is because magnetisation is 0. It's not so difficult to see. And well, the question is how fast does it go to 0? And what Eisenman, Bastian, and Fernandez proved in the 80s that it goes to 0 exponentially fast in the distance. Okay, which is basically the optimal for can get. So your model, if you look at it from very far away, it becomes like an independent system. Okay, so the subcritical phase is well understood. And as it turns out, the other cases where the model is well understood it's at criticality, which might seem somehow counterintuitive because it's at a very precise point that you don't know its value. But somehow if you have criticality and the dimension is sufficiently high, the model is well understood. And what is the idea here? There's a general phenomenon in statistical mechanics which says that if you take your model at criticality and the dimension is very high, is really high, your model behaves as the same model on a tree or on some sort of complete graph where you basically forget about the geometry. So when the dimension is very large, have so much space that you forget about the geometry of the graph. Okay? So this is a general phenomenon in statistical mechanics. And it turns out the case of the high-form model, the critical dimension about which you understand the model is 4. And what Eisenman and Froelich proved independently of each other in the 80s is that your 5-form model is, we call trivial at criticality dimensions 5 and above. So trivial in the sense of this Euclidean quantum field theory that I just mentioned before. So I told you that fields are interested in non-Gaussian theories. And 5-4 seems like a good candidate for a non-Gaussian theory, but as it turns out in these dimensions, the model is really Gaussian at large. So the scaling limit is some Gaussian field. I think it should be GFF, Gaussian free field, a continuum one with a certain covariance structure. Yeah, so this was proved in dimension 5 and above by Eisenman and Froelich. And much more recently, Eisenman and Dublin-Copano managed to go all the way to the critical dimension 4. And maybe you've heard that Dublin-Copano was awarded the Fields Medal in Mathematics a few years ago. He was awarded the Fields Medal, maybe not necessarily for this result, but for works in this area. So these are some very interesting and very difficult results to prove. And yes, we said one common feature of all these arguments for this proof is that the go through is you start from Ising, you prove something about Ising which is kind of uniform. So you manage to control your Ising model on all different graphs, and then you take some limit and you may get some results for Python. So this is the general strategy here. Just for culture here, I'm just mentioning briefly some other approach for the normalization approach, which I'm not an expert on, and yeah, maybe it doesn't make much sense to talk about this in more detail. Just in this case, you can set the model and at criticality when the dimension is very large and sufficiently large, at the expense of taking the parameter g that you have in your phi 4 model, this parameter here, g to be very small, so that you are somehow close to being Gaussian. So this is the only caveat, but you can get some very precise results of this using this method. Okay, so now in the remaining few minutes, I will just mention my results. So I want to mention two results. The first one is about the supercritical phase of the phi 4 models above beta c. So what we do is that we take some box, lambda n, and then we consider the average of the spins in this box. Okay, and we are working above beta c. And what we're interested in is large deviation estimates for this average magnetisation, for this empirical magnetisation. Okay, and as it turns out, the large deviations are different depending on whether you look at the upper or lower deviations. So if you're asking your magnetisation to be smaller than the expected one, then the deviations are exponential in the surface of the box that you're working on. And if you're asking for your empirical magnetisation to be larger than the expected one, then you get deviations exponential in the void. Okay, and in fact, this second result, in some sense, is not so interesting because it horsepower value of beta. So for this second result, you don't even need to work above beta c. So for beta, and just so different. The second one is the main result in this direction is the first one. And here I have some sort of absolute value in this magnetisation because I'm considering measure with free body conditions, so with zeros at the outside. And yet, in this case, you have some sort of symmetry of your models. So then your empirical magnetisation will be either close to the expected one or minus the expected one. So that's why I have an absolute value there. If you consider the plus measure, there shouldn't be an absolute value in this case. Okay, does this make sense? The first result? Some sort of large deviations. I'm sure that you're all familiar with that. You're all better experts than me in this kind of stuff. Okay, that's the first result. Then the second one, it's about the critical phase. It's a bit older one. It was published recently, and it says that at criticality in dimensions 3 and above, you have a continuous percentage. So the magnetisation at criticality is equal to 0. So indeed, even though you cannot calculate the value of beta c, you can say something about what happens in beta c. Okay.
So what do you have on? What do you have on? Must have some dirt on it, right? Like S2 file or something that you must have some functional equation on it, right? Like what do you have on that you can do?
No, so what we have is percolation. So we have this connection with percolation.
Also, yeah, P equals a half.
Yes, but it's not the only percolation. It's a different percolation model. So it's a percolation model on a random environment. So maybe I can explain briefly this. There are two representations. One of them is like this. So what is the idea is I'm going to do something very simple. So you have your spins, the take values over R, I'm just going to write phi as absolute value times the sign. Okay, so this I can always do. And now the thing is that once I condition the absolute values, what I get is an Ising model with so basically you have a random beta. The Ising model, you have beta times absolute value phi x, absolute value phi y. But okay, you condition on that, so you get an Ising model. And once you have an Ising model, there is some sort of connection to percolation using some sort of correlated percolation models, which are given like this. So you have a product of P over 1 minus P, right? If I were to stop here, if this was my definition of the model, then I will get 3 Bernoulli percolations. So I would have some edges which are present, some edges which are not present. But there is exact topological term in definition of the model, which is due to the number of clusters of connected components my configurations. Okay, so this is what makes the model correlated. And of course, again, you need to normalize by constant. And yeah, this is all in finite volume. So this is how you get your percolation model. And what is the idea behind the model? Is that what you want to encode in the model is whether two neighboring spins are aligned or not. This is what this really does. It's encode whether two neighboring spins take basically the same value. Okay, and then you can go from one measure to the other. So for example, if you understand this 2-point function, you can express it in this way. So basically, if you forget about the absolute values for a moment, what you are really saying is that the correlation from x to y and x and y is just the probability that x going to y in this percolation model. Okay, so if you can understand very well this percolation model, you can say something about the behavior spin model. So you go from something with more absolutely more analytical, this 2-point function, how this is, you can calculate, and you can take something geometric and use things from percolation theory to understand your model. And basically proving that atheticality magnetisation is 0 corresponds to proving that you have no infinite cluster for your percolation. And in general, for Bernoulli percolation, this is not an easy equation, so we know it when the dimension is very sufficiently large, but not all the way to dimension 3. And in the case of the Ising and phi model, you can go all the way up to dimension 3. So there's some sort of integrability, just a weak form of integrability I would say in the model that allows you to do. We don't have that much time to explain that in more detail. So I think I will stop here.
Your question yet again on the definition of the model.
Okay, yeah.
On the boundary condition, I understood that while the graph gets larger and larger, you want larger and larger boundary condition. Why is that?
Why is that? Well, this is some sort of artifact of what you can do with your hands there. So the more practical answer is it's what the intuition that I give you here is that this all comes from just more you can tell argument using this besides that your spins cannot be too large, they cannot be larger than some constant. And so that's how you somehow define your maximum value conditions. But a priori, of course, there is no big reason why you can do the state plus just a constant. Just more like an artifact of what you can do without getting into the fine details of the model.
So it's like the maximum growth that you can have.
Yeah, if you have such moments, then that's the maximum growth that you can have.
Yes, I had two. So one of them was just in the second to last slide, you were talking about the dynamical modeling spectrum that I missed what exactly you meant by the dynamical particle.
So right, so we then define exactly which dynamic I'm considering. So you can do basically Clauser dynamics.
Okay.
And we can get that the spectral graph is function the set. If you have values.
And the second question I had was, so obviously you're connecting, you're setting up 5-4 as like a kind of generalization of Ising, and this is kind of there are other ways, other generalizations of Ising I would think of, right, like POTS and the XY model. Can these be sort of connected with 5-4, or are there other kind of generalizations of those models that fall into the same kind of way?
Right, and yeah, there are generalization model without this connection to the model that goes through the complete graph. There's no very good reason to see, to see why this model should be more attractive than the other ones. As it turns out, the 5-4 model should behave the same way as Ising, in the sense that the critical response should always be the same, the scaling should always be the same. If you get X, Y, for example, and in dimension you don't have a phase transition, or you have this more exotic phase transition from exponential to formula decay. And yeah, I think you always, X, Y has a different scaling, even high dimension. So you have this connection to the H model, which gives you some exact.
Okay. There's not, sort of, people haven't thought about the POTS model, for example, and some sort of 5-4 like version of this stuff.
No,
There's no sort of way to connect these.
no, I don't think so. Because anyway, for the POTS model, the universal class changes when you go from one to the other, and also you don't even have a continuous phase transition when Q is statistical class.
Okay.
So you really expect a different behavior. So such if you had such a connection and you were a physicist, you would say that the two models are basically the same. Yeah.
Thank you for great short. I'm going to be completely honest. I was lost right in the beginning.
Okay.
However, this is a sort of technical question. Your results here are in some ways controlling something by the surface volume,
Right.
n to the d-1.
Right.
You've sort of defaulted to this expanding cube, or n to the d thing, and taken the limit. A very thick but obvious question is it necessary? So what sequence of expanding sets do you need to take to get this kind of result? Because at the moment, not knowing anything about what you've done, it looks very specifically like you've had to.
Right. So we took this. We defined our lambda in this way.
Yeah.
And yeah, to take the data. Yeah, that's not taking the detail, but basically, if you take any box that need to be of aspect ratio 1 in this direction, if you take like n tends to n box and you send n to infinity, you should have a similar behavior.
But if I just take any increasing set of sets,
Then
what fails? What is it that stops this from?
what you really use is somehow at some points is amenability. Is that the size of the boundary is much smaller than the size of the whole box. So as long as you take something which is very thick in one direction, then you're not able to get this.
Yeah, okay, so you need control over the boundary versus volume.
Yes.
Yeah, okay, thank you.